welcome to this explainer. You know, today we're tracing one of the most intense, literally dramatic manufacturing journeys on the planet. We're looking at exactly how heavy steel becomes gears. We're going to follow the life of a single gear, from its chaotic birth as raw molten metal all the way to its final form as a high-precision, nearly indestructible component. It's a process full of violent force, microscopic refinement, and intense heat.
I like to think of this as a hero's journey, but for materials. Our hero? Raw steel. And the villain it has to overcome is the extreme, absolutely relentless mechanical force it's going to face in the real world. To survive those forces, the steel has to endure a total gauntlet of trials. It's going to be crushed, cut, burned, and ground down to the micron. So what does it actually take to transform this raw material into a component that can power everything from an aircraft engine to a massive mining shovel?
Okay, let's dive into this. Here is our blueprint for today. First, from molten steel to blanks. Then, cutting the involute profile. Third, trial by fire, heat treatment. Fourth, precision grinding and finishing. And finally, powering the modern world.
All right, step 1. From molten steel to blanks.
Our journey kicks off in an environment of sheer scale and, frankly, violence. Before we can even worry about microscopic precision, we need brute strength, massive muscle. Just to put this in perspective for you, imagine 81 tons. In facilities like the EZTM plant, 81 tons of glowing molten steel is poured into a single massive mold. And that's just to form the starting workpiece for one giant industrial gear. Once that beast of a casting solidifies, it has to go through rigorous thermal treatment. Why? Simply to relieve its own internal stresses and improve its structural uniformity before we can even begin to shape the thing.
For forged gears, the process is just as intense. We heat up high-quality carbon alloy or stainless steel, right? Then, massive hydraulic presses literally crush or upset the stock, punching right through the center to create this glowing, donut-shaped preform. And this violent crushing isn't just about shape. It physically ensures the steel develops a proper, resilient grain structure. From there, it's transferred over to radial axial ring mills, which roll that hot donut out to its final massive dimensions. Bam! Now we have our blank, ready for the machine shop.
Moving on to step 2. Cutting the involute profile.
Okay, so now we are transitioning from the realm of raw muscle into the world of geometric, analytical precision. Time to cut some teeth. Now, the shape of a gear tooth isn't just some random triangle. It is heavily rooted in history and mathematics. Way back in the 18th century, the mathematician Euler defined what's called the involute curve. Fast forward to 1968, and companies like Gear were founded to scale this up for heavy industries like cement manufacturing. And today? Well, today we use advanced 5-axis CNC machines that take that centuries-old math and translate it into complex 3D spiral paths in literally a fraction of a second. Theory has turned into consistent, scalable reality. So what exactly is this curve Euler gave us? The involute tooth profile is a mathematically generated curve based on the rolling of a pitch line on a pitch circle. Sounds a bit abstract, right? But here's why it actually matters. This very specific curve ensures that as two gears mesh together, the transfer of power is perfectly smooth and consistent. It minimizes friction, it drops the noise level, and most importantly, it is entirely predictable and manufacturing friendly. Honestly, this curve is the absolute baseline assumption for speed and durability in our modern world. And this brilliantly illustrates how we actually carve that math into solid steel. What you're looking at here is a rack cutter. Notice how the straight trapezoidal edge of the cutter rolls against the circular gear blank. It's wild, because through this relative rolling motion, the straight lines of the tool gradually generate that complex curved involute profile right onto the gear tooth. It's this continuous, enveloping process that carves out the absolute perfect shape as the two pieces move in sync. Let's step onto the actual factory floor for a second and see how this builds in modern machines. First up, we have aggressive CNC roughing. On machines like vertical turning centers, you'll see a spindle whipping a heavy steel blank around at up to 3,000 RPMs while a cutting tool violently removes the bulk material. We're talking rapid, heavy-duty cuts. But once that bulk is gone, the machine seamlessly switches gears. Pun absolutely intended. For something complex, like a spiral bevel gear, it swaps to a tiny 1.5mm ball end mill. It makes these delicate, high-speed passes to create an incredibly smooth, fine finish. It really is a perfect balance of aggression and precision.
Which brings us to step 3, trial by fire, heat treatment.
Now, a freshly cut gear might look finished, but it's actually way too soft to survive out in the wild. It must endure the most dramatic transformation of its life, where the steel's microstructure is literally altered from the inside out. Now, what's really interesting about this slide is the sheer variety of ways we torture this metal to make it strong. Take carburizing, where carbon diffuses into the surface at around 900 degrees Celsius. It gives you brute strength and maximum load performance, but it carries a pretty high risk of warping or distorting the gear. On the flip side, nitriding infuses nitrogen at lower temperatures. It offers minimal distortion, making it perfect for high-precision parts, but it doesn't quite have the deep case strength of carburizing. And finally, induction uses intense electromagnetic fields for rapid, highly localized hardening.
This heat map shows exactly how these methods are deployed across different industries. Notice how dark red carburizing is for the automotive and aerospace sectors? Those are areas that demand maximum performance and massive load capacity. But look at nitriding. It's heavily utilized in aerospace too, specifically for precision components where dimensional stability is absolutely critical. You see, there is no universal superior method here. A gear going into a giant wind turbine needs a completely different trial by fire than a gear going into an agricultural tractor.
All right, step 4, precision grinding and finishing.
Surviving the fire is one thing, but that heat treatment often leaves the gear slightly distorted or with a rough surface scale. And that brings us to our final, highly meticulous phase. To get the gear back to its perfect involute geometry, we use the generating grinding method. The hardened gear gets clamped into a machine, and an abrasive grinding wheel is brought into contact. Here's the cool part. Both the gear and the wheel rotate in a perfectly synchronized motion, simulating the actual meshing of two gears. This generating action grinds down the hardened steel, stripping away material literally tooth by tooth, until that flawless involute profile is 100% restored.
But hey, we don't just take the machine's word for it. Every single gear must pass a rigorous post-grinding inspection. We measure the depths precisely on the pitch circle diameter. We scrutinize the exact curve of the involute profile to ensure it perfectly meets the mathematical standard. And we conduct lead measuring to confirm the precise helix angle. Basically, a gear has to mathematically prove itself right here before it can ever be trusted out in the real world.
And finally, step 5, powering the modern world.
All right, so the steel has survived the forging, the aggressive cutting, the searing fire, and the grinding. Where does it go now? Well, it goes out to quietly, relentlessly power human civilization. These gears are sent into the most extreme environments you can imagine. They go into Pratt & Whitney geared turbofan aircraft engines, spinning at terrifying speeds 30,000 feet up in the air. They become massive 1-meter-wide planetary gears inside wind turbines, designed to endure 20 straight years of shifting, unpredictable winds. You'll find them surviving the violent, jarring impacts inside Caterpillar electric rope shovels at open-pit mines. They handle the screaming 5,000 RPMs of a 3,400 horsepower Namco gearbox. And they relentlessly drive the marine propulsion systems of gigantic oceanic cargo ships. So what does this all mean? The crucial takeaway here is that our seamless, modern world is entirely built on the back of intense industrial violence. Next time you travel, whether you're taking off in a plane or just enjoying the quiet, smooth acceleration of a car down the street, ask yourself, how is that silent, effortless motion entirely dependent on the crushing presses, the aggressive cutters, and the fiery heat treatments you just learned about? It's a hidden mechanical world of absolute precision born from absolute extremes. Thanks for joining me on this explainer, and keep looking closely at the machinery around you.